We just finished solving a system of equations, actually two of them, with Gaussian elimination. There is a second method of solving a matrix, or using a matrix to solve a system of equations. It's called Gauss-Jordan, or Jordan, technically, elimination. And that procedure requires us to get the matrix in not only row echelon form, but what we call reduced row echelon form. When we talk about reduced row echelon form, it takes row echelon form a step further by saying that in addition to us having leading ones, if we have a leading one, that any elements that are directly above it should be 0 as well. Okay, so effectively, we would have something like this, and I'm just doing a 5-dimensional matrix. Why, I don't know, it's just what I wrote, but we would have, let's see, I'm miscounting here, 2, 3, 4. Okay, so in this example, we have ones along the main diagonal, and then off diagonal, both in the lower part and the upper part, it's 0. Okay, and then we would still have values over here. Okay, that is still okay to have values over here, but directly above it, we should have zeros. Okay, so how do we do this? Well, it's a little sensitive. We have to take row echelon form first, okay? So repeat all that work, then continue to do row operations, and almost kind of as we did row operations first, we kind of worked down the rows to make sure that they were all 0. Then we kind of work back up the rows, but we want to satisfy that condition that every entry above a leading 1 is 0. Okay, and then once we have it in reduced row echelon form, satisfying that all the entries above every leading 0 is, or every leading 1 is 0, then we translate it back and solve if needed. Okay, so here we'll do 2 examples again. Here's the first one. So if we solve the system using Gauss-Jordan elimination, okay, follow normal Gaussian elimination and then continue on. Okay, so first we write the augmented matrix. 1, 4, -2, -7, 1, -1, 1, -1, 1, and then include that bar as needed. Okay, and then I'm going to take, in my first step here, I'm going to take -4 row 1 plus row 2 into row 2. Okay, and so the first row remains unchanged, 1, 2, -1, and then we get 0, and -4 is 8, plus 7 is 1, and then -4 is 4, plus 1 is 5. Okay, so then this is row echelon form. That was nice, one step to get it in row echelon form, but now what I need to do is I need to make this entry, this 2, a 0. So what I'm going to do is take -2 row 2 and add it to row 1. Okay, if I do that, now the second row remains unchanged. And so -2 times 0 is, okay, so that just is going to remain a 1. Okay, -2 times 1 is -2, plus 2 is 0. -2 times 5 is -10. -10 plus 1 is -11. Okay, now and this would be considered reduced row echelon form because I have 2 leading ones, and above every leading 1 there's a 0. Okay, this one, I mean, there's nothing there, so that really doesn't count. Okay, so this is reduced row echelon form. And with this, I can then say that x is equal to -11 and y is equal to 5. See, now this takes out the work of doing that back substitution, so then I can just state the solution set. Solution set is -11 and 5. I should probably double check it just to make sure. -11. And I did mess up when I checked it, because then hopefully you caught this. Minus should be there, right? And so then I want plus 2. Still going to get the same matrix on the right, but it just changes this value to be 9. And so then I just have to change this and this. Okay, so always check your answers. All right, so next we'll move on to this next one. All right, so translate it into an augmented matrix. So 2, 7, 11, 11. I'm going to forego the dash line on this one. You can certainly include it if you want. 1, 3, 6, 8. Okay, now I really want you to pause the video, try it out, and when you're ready to see the solution, go forth. Okay, as a hint, I do recommend starting off by moving row 2 into row 1. All right, so at the end, I got 14 for x, -4 for y, and 1 for z. Okay, hopefully that matches yours. If it didn't, here are the steps that I took. And I'll zoom out just a little bit so we can get it all on one screen. So I started by switching the row 1 and 2 as I indicated first. Okay, next, what I did is I wanted to knock out these 2 entries, right? Because I don't want them. Those can't exist, so I take -2 of row 1 plus row 2, put that in row 2, and then I took row 3 minus row 1. Why? It will become clear, and put that in row 3. Mainly, I did it so that I would get a negative or a positive 1 here instead of a negative 1. You could have done it in the other order. Okay, so then I got this matrix. Here, I realized, okay, I want that 3 to be a leading 1, so I'm just going to switch row 2 and 3, which is what I did next. After this, again, I need to knock out that 3, so I put I took -3 times row 2, added that to row 3, put that in row 3, and got this. At this point, I'm in row echelon form, which is a good thing. To finalize this, what I ended up doing is, to get it in row echelon form, I had to knock out these values, right? Because above every leading 1, I need a 0. So I knocked out the values directly above the third leading 1 first. Okay, got that. And then after that, I knocked out the value above the second leading 1 and to obtain this. And then at this point, you can really just read off your solution, because this is saying x equals, is your dash line, 14, y equals -4, and z equals 1. Okay, so there we go. We solved the system using Gauss-Jordan elimination. So the question is this any more time effective than Gaussian elimination? Well, maybe, maybe not. Depends on the system. With a 2x2, maybe. 3x3, it's a little bit more work, but it gets you more practice with row operations.